Okay, hello everyone and welcome to our National Space Academy Takeover Week. We are taking over the National Space Centre's social media this week to talk to some really cool and really exciting space people who are doing some really cool stuff in the space sector. So my name is Nat, I'm from the National Space Academy and I am a physics teacher, and I am here with Dr. Anna Horleston from the University of Bristol, who is an expert on Marsquakes. So, hello, Anna. How are you doing today?
I'm great, thank you.
Good. So I just wondered if you could start off by telling us a little bit about yourself and what you do.
Yep, fab. I'm just going to try and share a few slides with you. So just a couple, and then I'll let people ask me questions. So hopefully this will come up okay. Give me a thumbs up. Okay, brilliant. So yeah, I'm Anna Horleston. I'm a planetary seismologist based at the University of Bristol, and I'm also part of the science team for NASA's InSight mission to Mars. And in fact, my primary role there is as co-lead of the Mars Quake Service frontline. So my job is to lead that team and help us find Marsquakes in the data we get back from Mars. So a little bit about me. I used to work with seismic data on Earth. So here's me in various guises scattered about the planet. This is Canada. This is the UK. This is Canada again. This is Morocco. This is the UK. And for those of a certain age, this is Steve Backshall. And I helped him test the magnitude of the earthquake created by a rock dropped on a car, which was the simulation of the stamp of an Argentinosaurus. So that was a lot of fun. So lots of different things we've used seismometers for on Earth. But now my data comes from here, which, as anyone who watched the Perseverance landing will look like, it will know, this looks like Mars, and it is Mars. This is our seismometer on the surface of Mars. And our seismometer is part of the InSight mission, as I mentioned. So this is the InSight lander pre-launch in the clean room at Lockheed Martin. So we launched in 2018. So this is the lander as they were preparing it. And if you can see my mouse, this is our seismometer here. So it's the lander's a few meters across, and it's a geophysical lander. So we were going there to look at all the geophysical signs of the planet to try and find out what's going on inside Mars. So this is one of our early photos as when we landed. So the seismometer is still here on the deck of the lander. This was literally taken 2 or 3 days after landing. And obviously now my seismometer is tucked under here, and this is to help protect it from the wind and the temperature on Mars. So that's where my data comes from. It's a really sensitive seismometer, and we can pick up some beautiful signals from Marsquakes. So this is a classic, beautiful Marsquake. This one actually looks quite like an earthquake. So what you're seeing here, we have 3 components to our seismometer. So we can measure the motion of the ground up and down, north, south, and east, west. And what you're literally, this wiggly line represents how much the ground is moving up and down where our seismometer was placed. And you can see the primary P waves, compressional waves, and the shear waves arriving here. So just like you might see on an earthquake. So this is one of our best quakes, and it was really exciting when we saw this back in 2019. And we can locate these quakes, or at least a few of them. So here's a map of the whole of Mars, and we zoom in on this square here, and you'll see InSight is here on Elysium Planitia, and these are the locations of 2 of our best quakes, the one I just showed you and another one. And you'll see on this map we've drawn in some red lines. These red lines represent the fractures of Cerberus fossae. For those who don't know, Cerberus fossae is an area on Mars where there are fractures in the ground up to 1,000 kilometers long and only a few hundred meters to kilometers wide. So really narrow cracks all the way across the surface of Mars, and our best quakes locate to back here. So my job is to find these quakes and work out where they come from and work out what that means for the inside of Mars. So I'll stop sharing now, and then we can go to questions or anything else.
Great, thank you so much, Anna. So I was wondering, could you maybe tell us a little bit more about the InSight mission itself?
Yeah. So the lander, it's a geophysical mission. So geophysics is a really broad subject, obviously. So we went there with 3 primary goals. So we wanted to measure the seismicity on the planet, which basically means finding out all the Marsquakes we can find, recording them, and then trying to work out the structure of the planet from that. So we want to know how big the core is. Is the core liquid or solid? Obviously on Earth, we've got, a solid and a liquid core, but we don't really know exactly what we've got on Mars. So we wanted to work that out. We wanted to look at the structure of the mantle and the crust. So actually the entire internal structure of the planet. So we got seismology for that primarily, but we also have what's called RISE, which is the rotation and interior structure experiment, which is a bit like a really cool GPS tracking device. In fact, it sends out a high frequency radio signal, and by recording the time difference between when that was sent and when we recorded it and the Doppler shift on it, we can work out exactly where Mars is in its orbit and whether it's wobbling or not. And by tracking that wobble, like if you have an egg and you spin it, you have a raw egg and you spin it, it spins differently to a hard-boiled egg. And the same with Mars. Planets move differently if they have liquid inside them. So we can use the RISE experiment to help tell, again, what's inside the core. We also wanted to measure the heat flux. So I don't know how many people have been following the mission, but we had something called the MOLE, or the heat flow probe is its proper name, but so our nickname is the MOLE, which was supposed to bury its way down 5 meters into the planet. And it was supposed to measure the temperature. And unfortunately, the sand on Mars is not playing ball. And so it's not managed to bury itself, which is really, really disappointing. So we haven't quite managed to measure the temperature. We've measured it at the surface, but not 5 meters down like we'd hoped to. And what is the other thing we're looking at? Temperature? Seismicity, that's it basically. So the structure of the planet, the size of the core, and that. And we're also looking for meteorite impacts as well. And to help us do that, so we have the seismometer, we have the RISE experiment. We also have temperature sensors and wind speed and direction sensors and a pressure sensor, so that we can find out what the atmosphere is doing as well. Because as you saw, our seismometer is right on the surface. So the wind is blowing past it and the temperature changes by like 100 degrees every day. So we have to try and work out what's being caused by wind or temperature and what's actually coming from inside the planet.
Sounds like there's quite a lot going on then. There's a lot to figure out there.
There's a lot going on, yeah.
That links quite nicely into one of the questions we've had from one of our space engineers. Well, there's 2 questions. So the first one is from Kane, one of our space engineers, and he has asked, what is the difference between seismology on a foreign planet and on Earth? So how is it different when it's on a foreign planet?
Okay, well, hi Kane, that's a great question. So on Earth, I guess the simplest thing is to say practically it's a whole lot harder. Obviously, we've got to get the seismometers there, but once we're there, obviously on Earth, we have thousands of seismometers. I mean, literally thousands scattered all the way around the planet. We've got one on Mars at the moment, and no one seems to want to send another one, which is very sad. I'd really like another couple up there. With one, it's a lot harder to work out where things are coming from. And obviously, we can only either hear things that are very local to us or things that are very big. So obviously on Earth, we can pick up all the tiny little tremors from all sorts of different things. Secondly, I guess we don't know. So one of the things we rely on Earth is that because we have centuries now of data, seismic data, we know a velocity model for inside our planet. We know the velocity model inside Earth. So if we see a P wave and an S wave, we travel at different speeds through the Earth, we can tell exactly how far away that quake was. Whereas on Mars, we've had to say, well, we think it's these rocks. So we've assumed velocity models, and we've created thousands of velocity models. So every time we have a quake, we then test those P and S travel times through all the different velocity models to try and work out where it came from. And we go, well, it fits best with this 300 models. So that's probably where that quake comes from, which is why if you saw that picture, there was quite a large ellipse of where the event could have been. It's because we have loads of models. So we still don't know the perfect model. So we're kind of trying to find the quakes and find the model all at the same time. So that's another problem. And I guess the other problem is the simple fact of the practicality, like getting the seismometer there. Like on Earth, I used to travel a lot, so I'd be able to go and put an instrument somewhere, and if it didn't work, either I could go and check it, or one of the people who lived in that country, if I wasn't due to come out, could go and look at it. Whereas on Mars, it's like if it stops working, we have to try and use a robot to think about why it might not be working. And that's, but if it breaks, there's nothing we can do to fix it. So, or at least there's only a certain amount of things we can do. So yeah, there's a whole range of things we have to think about. This is a really good question. Oh, I should also mention the gravity. Obviously Mars has different gravity to Earth. So we had to completely redesign our seismometers because everything's tested to work at 1G here, and Mars has a fraction of that. So yeah, we have to completely re-engineer everything as well.
Oh, great, thank you. So again, that leads nicely into another question we've had. If you're able, would you go to Mars to do your work there?
Oh, me personally, I have to admit, I think I'm getting a bit old. My son would go at the drop of a hat. I've got an 11-year-old and he is desperate to go to Mars. Me, myself, I think, I don't know. You know what? If you told me I could get there and back, I probably would. I think my fear at the moment is the getting back part. I'm not ready for a one-way trip to Mars just yet. I mean, give me 20 years and maybe I will be. But right now, I wouldn't go unless you could get me home again safely. So if you can engineer that for me in the next 5 or 10 years, that would be fab. And then I'll go, yeah. And I'll take a whole bunch of seismometers.
Put them everywhere. Seismometers everywhere.
Really.
So what advice would you give to your son then if he wanted to particularly stand out and he wanted to get into the space sector? What sort of advice would you give for things that he could do to help him stand out compared to other candidates?
You know what, it's a really hard question. I think obviously you need to excel at your school subjects, but I also think you've just got to be an interesting person. You need to be interested and interesting. You need to go out there and find what you love. I think people often wonder, I've had quite a weird career path. I started studying astrophysics and then I switched to earth sciences and did all of that. And now I've kind of come full circle and I'm doing both. But all the way along the way, I've kind of chosen jobs that I really wanted to do, that they were just interesting. And it's not a case of saying, oh, I want to do this, so I'm going to study physics and maths, and then I'm going to do an engineering degree. I mean, those are very worthy things, and those will be very useful. But along the way, do what you love and what you find passionate. And that's what I find exciting. That's what I'm going to tell him to do. He loves climbing mountains, so we go and do that. That doesn't really help, but it's just something that he likes to do, so we do it. So, do what you love and be interesting. And that's not easy, but,
No, it's a really fantastic piece of advice. I think that's the key thing, isn't it? If you pursue those interests both in school and outside, you're going to have a whole base of things when you're applying to talk about.
Yeah,
that's really good. So I actually have a question. I'm really interested in all of the traveling that you did with your job. So I was wondering if you could tell us a little bit more about that.
Yeah. So I guess I first started traveling while I was doing my PhD, and the travel I did then wasn't actually for my research, it was just for my supervisor's research. So I just went to Scotland a few times to do field work there. But then my next job was working for Seis UK, actually based in Leicester. So I lived in Leicester for a few years. And my job there was to help run the seismic equipment facility for one of the Natural Environment Research Council's equipment pools. So that sounds like a lot of words, but basically we had 400 seismometers, and academics from across the UK could ask to borrow our instruments to go and do their research projects. So I got to go to, I went to Italy. I put 100 seismometers in one field to measure a landslide, but got to eat lots of amazing Italian food. I went to Hungary, where we put them all around the Pannonian Basin. So we drove all the way around Hungary and just about into the Ukraine, and we put out seismic stations all around there. So we link up with local people from their local institutes who travel with us and help us out with all the deployments. So I went there. I went to Chile. I spent 3 weeks driving a 4x4 up and down Chile. Absolutely amazing. So remote and rugged. I went to Wyoming. I went to Iceland. Oh, I loved Iceland. That was brilliant as well. Again, I wasn't allowed to drive the 4x4 across the glaciers, but I'd done all the training and I was like, oh, I so want to do this. Where else did I go? I've obviously been to Morocco. It's a whole lot of fun. There's a lot of places I didn't get to go as well. So I was supposed to go to Ethiopia, but I was pregnant with my daughter, so I couldn't travel at that point. But and one of my colleagues has now been to Antarctica as well. So just amazing. I mean, we've put seismometers in so many different places, and it's just a whole lot of fun. I mean, you always link up with someone from a local institute, so you've got some on the ground knowledge, and then you ship out all your equipment and it arrives hopefully before you do, and you just get to adventure basically, because you almost always have to deploy the seismic stations on somebody's land. So you may be like in Chile, we would literally just drive down this deserted road and find a farm and say, can we borrow a corner of your field to put this instrument in? And then you'd explain what you were doing. And, we were trying to look at the outer core boundary, actually. So we were looking at the, deep structure of the Earth, recording earthquakes from the opposite side of the planet. And we explained all of this, and you sit and have a cup of tea with them, and then you go out in their garden, you dig the hole and put the seismometer in, and then you drive off, and then you come back 6 months or a year later to download your data again. And it's a wonderful way to see the world and to meet people. So yeah, thoroughly enjoyed it.
Well, that sounds really exciting. So you've been all over the world and you've put seismometers in really cool places, probably the coolest of which was then Mars. So how did you make that transition from, did you say you started in astrophysics and then you went to the...
Yeah, I've had a pretty circuitous career path, let's say. So I went to university, so my undergraduate degree is physics and astrophysics. So I've got an undergraduate master's in physics and astrophysics, and then in my fourth year of that, we were offered the option to take the seismology lecture course from the Earth Sciences department, because it's, seismology is basically the propagation of waves, which is physics, which, it's all the same stuff. So they let a few of us from the physics department come down and take that course, which I absolutely loved. And again, follow what you love. So I really enjoyed that. And I chatted with the lecturer and he said, well, I've got a PhD open if you want to apply for it. So I was like, well, okay, what else am I going to do for the next 3 or 4 years? So I spent 4 years studying subduction zones. So I didn't get to go there, but my data was coming from the Aleutian Arc off Alaska and from the Marianas Islands above the Marianas Trench. So I did my thesis on that. It's on a shelf over there, but I can't make my finger about there behind me. Then so I spent 3 or 4 years studying that, and then I took the job at SEIS UK, so I got to do all the exciting travel. And then I had children who I decided to take time off work. Traveling wasn't that easy with the young kids, and I wanted to devote my time to them. That was my choice. So I spent a lot of time with them. And then I was asked by some people I'd worked with when I was at SEIS UK. I worked with some people who were then back at Bristol, and they needed someone to put instruments in Morocco. So this particular lecturer, he'd got a grant, a huge grant, to go and study Morocco, and he said, well, I need someone to buy me equipment and put it in the field. And I said, well, I know how to do that. That's what I've been doing for the last 4 years. So I went and started working for him again, just part-time when my kids were small, and I went off to Morocco and put his instruments in, did all of this. And I'd been doing that. And then I worked on fracking. So I was working, the British Geological Survey had a grant, and Bristol University were part of that. And we went and put out the monitoring arrays in Lancashire and Yorkshire pre-fracking. So we were doing the baseline monitoring there. And that was quite a lot of fun, and it was close to home, which was easy for me to get to. And then I saw the advert for this job, and it was again at Bristol with people I knew, and it was like, this is seismology, and it's on another planet. And I've looked at Mars, obviously, in my undergraduate degree a little bit, not much as I now know about it, but it just seemed like it came at the perfect time for me, and it was the perfect job. It's like I genuinely get to work on the two things I love. It's space and seismology. So and again, it was one of those things where people say, oh, but did you plan this from when you were 5? And it's like, no, of course I didn't. I kind of thought maybe it'd be cool to go to the moon, and that's partly why I read physics and astrophysics when I was 15, 16. But to think that I would have ended up working on this mission, that's just something I couldn't have planned for, because this mission didn't even exist then. And even it did, it was in such a different guise, and it was supposed to launch 2 years earlier, and it got delayed, a bit like the Rosalind Franklin mission has. So sometimes you can't make a mission, a life plan that includes something like a space mission. You've just got to go with the flow and do what you love.
Yeah, that's a really great message. I think that's something that I definitely want to try and convey to our space engineers. If you follow what you enjoy, the likelihood is you'll end up in a job that you enjoy.
Yeah.
So we've had a question from our comments. It's from Sky, and Sky has asked, what do you find to be the most rewarding aspect of your job?
Wow, that's a fab question, Sky. Right now, I actually love the outreach side of it. I love this kind of thing. Thanks to this job, I mean, I used to do quite a lot of outreach, but now I've done so much more. And in fact, lockdown has almost made that easier, because now, rather than me having to travel across the country to go to a classroom, I can do it via Zoom, just like I'm doing for you now. So I can literally sit here and I can feed my kids lunch in half an hour, but I can have given a presentation to however many people. So I love doing the outreach. I do love the fact that we found Marsquakes. I mean, that is just like, wow. And my job literally is, so the data comes down from Mars pretty much twice a day. And it comes down with maybe a 6 to 12 hour delay. So this morning I was looking at data that was recorded on Mars last night. And to know that I can do that, even so, look out the window and see Mars, and it's so, it's like so distant, it's literally a dot in the sky. So that sense of, wow, I'm part of something that created something that lets me find Marsquakes, literally find quakes on another planet, which we are using to find out what's inside that planet. That blows my mind in a way. But I guess, most rewarding is the buzz after I've given a good outreach talk. But they're not always good, but a lot of them are.
Well, great. Thank you so much. So what does, just out of curiosity, what does a typical day as a Mars Quake scientist look like? I was just wondering.
Well, I guess a typical day at the moment is actually, it's not that different. A typical day used to be drive to the office and then look at the data. But at the end of the day, the data comes from Mars and it goes via a server at JPL to a server in Cannes in France to a server at ETH, where I get my data from in Zurich. And then I log into it. So actually, I can look at my data from anywhere. At the moment, my day mostly involves in the mornings. I look at data and I'm doing some research. So obviously, I do some data processing and some Python coding. And then the afternoons, I often have meetings because of the time that, obviously this is an international mission and it's led by JPL in Pasadena. So they're 8 hours behind us. So we have a lot of meetings scheduled for kind of starting at 3 or 4 in the afternoon, because they get up. Even that is 7 a.m. to 8 a.m. for them. So it's an early start for our Californian colleagues. But so we'll have a lot of meetings in the afternoon. So the way the mission is worked, we have overarching science meetings where we discuss major strategy, but then we also have small working groups. So we have a group that discusses all the stuff that's going on with the atmospheric data, so the pressure and the wind. We obviously have the seismic data, so we have our own Mars Quake Service meetings and events meetings where we discuss things. We've then got a group that look at the deep interior of the planet. We've got a group that looks at the surface of the near surface of the planet. And we've got another group that looks at just how we're processing the data to find things out. So almost every day there's a different meeting to be joined, and that was always done remotely anyway, so that used to be WebEx and it still is. And then on the good days, when we could travel, we would meet every 3 or 4 months and we'd all go and meet for a week, and we'd vary where that was. So sometimes it would be Pasadena, sometimes it was in Paris, sometimes we went out to Austria. We were due to have a meeting in London, actually, which would have been easy to get to, though far less exciting than getting to go to California in February, which is really nice to see some winter sun. So we'd then go and have a week, and we'd literally spend the whole day on that week. We'd meet from 8 till 6-ish in meetings, and we'd again share all our results and have breakout sessions where you can go and chat and look at posters. So scientific conferences, I don't know how many you've done, where you can take a poster of your research, and that's a great way to share your research with other people, because if you've made it into a big poster, all your results are there and then people can come and talk to you about it. And in some ways it's easier than giving a talk where you get your 10-minute slot and then you have to get off the stage, whereas with a poster you could spend like 3 hours stood in front of it talking to different people as they come and go. So we do quite a lot of poster sessions as well in those. So yeah, it's a varied job, I guess, and every day is slightly different. And then every now and again I do something like this, so and that takes up my morning instead, which is a whole lot of fun. So.
Oh, that's great, thank you. So we're going to finish on quite a big question, but our last question for you, it's one that's come up quite often, but what do you think is one of the biggest challenges that your field faces going forwards?
Wow, I'm going to take my field as planetary seismology, not Earth-based seismology. So if I stick to just seismology, I might have to veer into planetary missions in general. I guess there's the financial side of it. where does the money come from? And especially, for example, at the moment, I am not unaware of the fact that right now, COVID is probably something we should fix rather than putting seismometers on other planets. I hate to say that because I really want seismometers on other planets, but actually it's better to humanity right now to build more, to fix COVID first. So a lot of space missions have a lot of spin-offs that are really useful here on Earth. So I do think we should keep investing in space. I think that's really important because the spin-offs are amazing. And I would love to know more about what's going on in other planets. So for us, it's going to be funding. Obviously, at the moment, for Mars, everybody wants to look for life, which is very worthwhile, and it would be really fascinating to find life on Mars, and it would be quite cool to go and see if we can inhabit another planet. I'm a bit scared of this idea of we can just planet B option. I don't see it like that, but the idea that we could figure out the life support systems for something else on another planet, that is pretty amazing to me. I scuba dive sometimes, and even that, trying to keep you alive underwater seems scary enough. Like the thought of keeping you alive in a planet that is minus 100 degrees and doesn't have any oxygen, it's like okay, and is being pummeled by solar radiation. It's like that's a whole different level of ingenuity required to keep you alive. So I guess you asked what the problems are. The problems will be money, basically. And can we persuade the industry to link with academia? Because obviously we've got the likes of Elon Musk with loads and loads of money, and SpaceX is amazing. I was in absolute awe watching those launch and watching the boosters come back down and land perfectly. It's like, that is just, having grown up with shuttle launches and disasters, the terrible cost to humanity, to see these things come together now. But there's a big part of me that goes, Elon, can we not just send a seismometer to Mars, please? Send some more. Do some more science out there, please. Not just rockets into space and blinking Starlink satellites that obscure our observations. I'm rambling, but I would say money is probably our biggest hurdle.
Great, thank you. And I know I said that was the last question, but very quick question. Which planet would you send a seismometer to next if you could?
Well, that's a really tough one. I'd really like another one on Mars. After that, it would be some of the moons out in, the terrestrial moons or Ceres or something like that. Stick them out on Titan or something. That would be cool, just to see some other things. I don't think we can make one survive on Venus. Mercury would be interesting, but again, it's a real challenge. So I don't know. Let's go see some exoplanets.
That would be good, wouldn't it? Great. Well, I look forward to talking to you when you've got a seismometer on some of the moons further out now.
I look forward to that day too.
Oh, well, thank you so much for your time today. It was an absolutely fantastic talk. And just a reminder that we've got these talks going on all week, so please join in. You can get in touch with us at National Space Academy on Twitter, follow at UK Space Academy. If you have any careers questions, please feel free to go to our website and you can submit them there. Once again, thank you very much, Dr. Anna Horleston, and thank you very much everyone for watching.
Thank you for joining us.